Hey guys, welcome back to my channel. Today we're gonna dissect a Python library that I came across recently, which is MovingPandas. So we're gonna apply and explore all its features through this app here about shark tracking around this small island in Mexico. So if you're interested to see what MovingPandas has to offer, just keep on watching. All right, so Moving Pandas is a library mostly used to analyze data about some object or phenomenon that moves through both space and time. So basically, data that has a location related to a timestamp. So, for example, here today we're going to use some shark tracking data around the island of Guadalupe that is provided by the Sea Open Scientific Data publication and that we can find directly on their website. So this is what I imported here. I did some manipulation, as you can see here, and created a geodata frame object out of it, which I displayed here. So basically, we have 10 white sharks that are identified with their own IDs, for which we have some stats like the sex, length, and a time series of their movement through time. So each timestamp that you can see here is linked to a point geometry here that represents the shark's location at that time. Now, just for the sake of not cluttering the charts or maps with all these paths, I created a selection widget like so here. So this new component was actually in the latest update of Streamlit, which if you are interested, I reviewed all the new features in one of my last videos. So here we have the selection button here, which if I select 1, 2, 3, these are the selection of sharks. All right, so first thing you do when using moving pandas is creating a trajectory class object. Now, since we have more than one trajectories, so aka 10 shark path, we actually need to create a trajectory collection object where we specify the trajectory ID here. So when we print the object, we can see that the trajectory collection has 10 trajectories. Once we have that, we can use the various methods that are associated with this class, like adding the speed, the distance, and the time delta. Now, to view the underlying geodata frame that it creates, you just use the 2.gdf method like this. And it creates this data frame here, which you have the added speed, the distance, and the time delta for each timestamp. Now, with this added info, we can calculate some stats about the shark's journey. So here we have calculated the total distance traveled, the average speed, and the time elapsed from start to finish of the tracking device. So all these metrics were calculated with, again, the added variables here. So using the same info, I also created a plot depicting the speed distribution for each shark using the Plotly Express library. So as I said, you have all these sharks here with their distribution of speed. As for the next few sections, we're going to see how to create a handful of layers, each with their own properties. So first here we have the actual pings that the tracking device recorded on each shark, and that uses the same dataset that we have just seen earlier. So to create the actual map, I'm using the Folium module within the leaf map library. So you just have to use the add_gdf method and input your dataset and input a layer name. And if I zoom in on the map here, we can see the actual pings of all the locations of the sharks at each timestamp. Now, if we want to display the shark path in a continuous way instead of individual pings, we can do so by first using the toTraj_gdf method that creates a line polygon for each trajectory. So here you're actually seeing a polygon geometry, but that's only because I have transformed the line string into a polygon using a sum buffer. So using this geodata frame that I input in this Folium map here, we can see, if I zoom in again, that the individual pings are now in a continuous line. Another transformation we can do with the trajectories is to simplify them if we feel like having all these timestamps is a bit too much. So here, for example, we're simplifying the trajectories so that a 30-minute gap is considered in between each ping instead of only 1 minute with the original dataset. So to do so, we're using the min time delta generalizer, and then we're outputting the GDF, the geodata frame object through this method here. So using this newly created geodata frame, we can input it into again a volume map to visualize it. So as you can see here, the paths are very simplified. They cut corners a lot. So this is the kind of transformation you can do using this feature. One other way of transforming the path is using a smoothing technique like the Kalman one that I've used here. So this basically rounds some rough corners for a smoother finish. The process is basically the same. You're outputting the GDF object and then inputting it into a volume map. Now we cannot see really the difference compared to the original path, but yeah, maybe I could have changed some parameters in the feature here to have a greater difference. But yeah, another cool element you can derive from these functions is the area that the individual pings cover. So now, for some reason, you cannot use this function with a trajectory collection object so that we have created earlier. So I had to loop through all these, all 10 shark paths to get all the areas. So here we're extracting the area using the getMCP function and wrapping all of these data sets into a geodata frame, which looks like this. And when you display it on a map, it looks like this. So you have each areas. Last item I wanted to cover before jumping on the app was the aggregation feature. So the MovingPandas library lets you create a trajectory collection aggregator that allows you to aggregate a bunch of trajectories together in a certain way. Here I'm using the getClusterGDF method to extract the number of pings in a 100-meter radius, which creates this data frame here. You have a point with a weight and a location. So this type of data will then allow us to create a heat map, which I created with the, again, leaf map object. And the heat map is about hotspots where we most often see sharks through time. So for some reason, it is not at the right spot. So if I zoom in here, you see the heat map. All right, so let's see what we got after merging all these features together. So as I said earlier, let's select a set of sharks so that we can actually see something on the map. So for instance, let's select the IDs number 1, 2, 6, and 7. And when we do, all the components appear on the app. So it seems we have selected 2 male and 2 female sharks with relatively the same length. We don't necessarily have the same period of time of data, but it's interesting to see that for both sharks, where the data spans over 2 days, it seems one of them has traveled a much longer distance. The shark's average speed seems to be relatively the same, apart from that one female shark here, which we can clearly see in the speed distribution here, where this shark has slower speeds compared to the others. Another interesting observation is that there seems to be two distinct distribution of speed for all sharks, one in the lower end in the speed range around 5 kilometers per hour, and another peak around 20 kilometers. So I've done a bit of Googling. These bursts of speeds are most likely generated when sharks are attacking a prey, which is pretty logical. Now, on the right hand side of the screen, we have all the layers that we have created earlier. Now, it may seem a bit busy here as all the layers are displayed. So let me just keep one of them first. So here we have the individual pings. It's interesting to see the kind of loops that these sharks make through their journey in the sea. It seems that the green one has traveled a long way alongside the shoreline and only in 2 days, as you can see here. While for instance, the orange one or the red one seems to have stayed in the northeast of the island during the whole month of tracking. We can also, of course, visualize all the path layers. So this was the ping one. We had the path layer, which links all the pings together to have a continuous line. We have the simplified version, and of course the smooth one, which again we cannot clearly see a difference in this case here. So you get the gist. So we also created the area layer. Now maybe it would have been interesting to actually remove the area where the polygon overlaps with the island to only see the portion of water where the sharks have been. But yeah, it's still interesting to see the range of distance that these sharks travel, and we can see even better the difference of area between the sharks. So of course we have the big area for the green one and the small area, for instance, for the red one. Last layer that we have created is the hot spots. Actually, for this one, let me just add all the sharks together to have a better view. As we see here, there seems to be a concentration of pings in this sort of bay area, which is pretty logical for sharks. Now, I'd be very interested to see this same view with a much more complete data set of sharks, and not only the sample of 10 sharks that I have for today. So yeah, that sums up pretty much what I wanted to show you guys today about the Moving Pandas library. I feel like this library could be very useful in a bunch of use cases. Of course, this one is just an example. I really like the wide range of features that it offers, and I'm sure I'll be using it in the future. That being said, I hope you guys enjoyed this video. Don't forget to like, share, and subscribe, and I'll see you in my next video. Bye, guys.